Hi everyone, and welcome to Team 3's project video. We're excited to share our progress on building a reliable orientation sensor in collaboration with JCB. Along the way, we'll also explore what quaternions are and how they compare to Euler angles. Get ready for an exciting dive into engineering principles, orientation tracking, and some cool tech concepts. Let's get started. For this project, we used an Arduino Nano Every and a BNO055 sensor. We began by measuring Euler angles, yaw, pitch, and roll, right from the sensor. This gave us a baseline of the data Adafruit's built-in filters were already smoothing out. From there, we explored concepts like the Kalman filter, which helped refine and stabilize the output data even further. Next, we graphed the quaternion data. Unlike Euler angles, quaternions introduce an extra dimension, which makes tracking our object's orientation much more accurate. Quaternions are made up of 4 components, one scalar value, w, and 3 vector components, x, y, and z. Together, these represent the rotation axis and angle in 3D space. This compact format ensures smooth transitions and avoids issues like gimbal lock, even during complex movements. In our JCB collaboration, we used quaternion data to calculate precise rotations, converted it back to Euler angles, and displayed it on a curve graph to simulate the position of a scoop. This step showcased the flexibility of quaternions in tracking orientation accurately across multiple dimensions. Euler angles are a simple way to describe rotations, breaking them down into roll, pitch, and yaw. However, they come with a major drawback, gimbal lock, where 2 axes align, causing 1 degree of freedom to disappear. Quaternions solve this issue by offering smooth global orientation tracking in a compact 4-value format. They're especially handy for 3D applications like animations and transformations. For the first phase, we focused on comparing the raw Euler angle data from the BNO055 with data smoothed by our Kalman filter. On the graph, you'll notice the unfiltered x and z axes are quite shaky, while the filtered y-axis remains smooth and stable, highlighting the filter's effectiveness. To take things a step further, we fused accelerometer and gyroscope data from the BNO055 to calculate quaternions ourselves instead of relying on the Adafruit filter. For this, we adapted the Madgwick filter from xio.co.uk. Here's the result of our sensor fusion, displayed on a graph. As you can see, the calculated quaternion data is just as smooth, if not smoother than before, thanks to our filtering approach. So, what did we learn? Quaternions combined with advanced filtering offer smoother and more accurate orientation tracking. While Euler angles are helpful for simple rotations, they struggle with complex 3D movements. Quaternions, especially with the Madgwick filter, excel in dynamic environments, making them the better choice for real-world applications. This project showed how engineering principles and practical tools like Arduino and the BNO055 sensor can work together to achieve amazing results. In the future, techniques like these could advance autonomous machinery, robotics, and even virtual reality. Thank you for joining us, and we hope you enjoyed exploring the world of orientation tracking with us.